Hi everyone, this is Sir Farhan. Let's start Cambridge International AS level paper, paper 2, May-June 2024, variance 21. The duration of this paper is 1 hour 15 minutes and we need to attempt all questions, all right? The total marks for this paper is 60. You may use the calculator and in order to uh, draw any diagram or graph, you need to use HB pencil for that, all right? Let's start with the first question. Let's see what we have in it. Seems like the first question belongs to group 17 element. Okay. The elements of group 17 are called halogens. Halogens हम इसलिए कहते हैं because they can make salts. Also called halogens because they can make salts. Complete table 1.1. We have chlorine, we have bromine, we have iodine. The color at 293 Kelvin. 293 is basically the room temperature. Chlorine has a yellow-green color. Or just green also. Bromine has a brown color. And iodine at room temperature and pressure shows black color. Sometime in some books, dark gray also, okay? State the trend in volatility of halogens, chlorine, bromine, and iodine. Explain your answer. So, well, the volatility of halogens decreases from chlorine to iodine. Chlorine to iodine. And the reason for this, that when we move from chlorine to iodine, number of electrons increases. And when number of electrons increases, obviously strength of van der Waals forces increases. Van der Waals forces are also called temporary induced dipole-dipole forces. All right. So, as the number of electrons increases, the strength of van der Waals forces or temporary induced dipole-dipole forces increases, and therefore volatility decreases. In the next part, in part C, iodine is made by reacting bromine with sodium iodide. Construct an ionic equation for the reaction of bromine with sodium iodide. By the way, we have done this equation in class, and according to this, it's also called displacement reaction because bromine is more reactive than iodide, so it can displace iodide in the form of iodine. So it's basically a displacement reaction. Displacement reaction is also called redox reaction. Why redox? Because bromine is an oxidizing agent while iodide is a reducing agent. So we can say that it's a redox reaction. Anyhow, we need to make an ionic equation, guys. So you have to be very, very careful. Examiner needs an ionic equation from you. So bromine will remain as it is. reacting with iodide ions, converting into iodine and two bromide ions. Okay, examiner doesn't need state symbol, so we don't need to mention it. Let me clear one more thing. See, this is bromine, and see, this is NaI. All right, that is sodium iodide. Now this bromine reacts with iodide and displaces it in the form of iodine, while sodium and bromine reacting together, converting into sodium bromide. How many bromine here? 2. So we need to balance 2 bromine. How many sodium here? 2, right? And we need to mention 2 sodium here as well. So it's a balanced chemical equation. We know that sodium is a spectator ion. So spectator ion always cancel out with each other. So the final equation would be like this. This is Br2. This is 2 iodide converting into I2 plus 2Br minus. So that is the concept behind this ionic equation, which I've written it over here, right? State the role of bromine in the reaction, explain your answer. Well, all halogens are oxidizing agent according to my lecture, which means bromine is acting as an oxidizing agent here because it oxidizes iodide into iodine and reduces itself. So bromine is an oxidizing agent. Because it oxidizes iodide into iodine and reduces itself. Into bromide. Okay. In the next part, concentrated sulfuric acid is added to separate sample of containing equal amount of NaCl, NaBr, and NaI. All three sample initially react to produce the hydrogen halide. Okay, let me show you. This is sodium chloride. It is reacting with concentrated sulfuric acid, converting into sodium sulfate and HCl, and you will get the misty fumes of HCl. Okay, so when we talk about sodium bromide, it is reacting with sulfuric acid, again converting into sodium sulfate and HBr, and obviously HBr has misty fumes. Last but not the least, sodium iodide is reacting with concentrated sulfuric acid. So it will turn to sodium sulfate and hydrogen iodide. So initially in these reactions, sulfuric acid is acting as an acid only. All right. In these reactions, sulfuric acid, concentrated sulfuric acid is not acting as an oxidizing agent, by the way. All right. You have to remember this. Write an equation to describe the acid-base reaction that occurs when concentrated sulfuric acid reacts with NaBr. So that's the equation. We need to write it here. So it's basically sodium bromide. It's reacting with concentrated sulfuric acid, converting into sodium sulfate and misty fumes of HBr, that is hydrogen bromide. Okay. Then the next part of the question, deduce which sodium halide produces the largest percentage yield of hydrogen halide when concentrated sulfuric acid is added. By the way, concentrated sulfuric acid is acting as an oxidizing agent. All right. Explain your answer by considering the relative reactivity of the halide ions as reducing agent. Identify of sodium halide. Uh, you know that sodium chloride would be the right answer here because chloride is a weaker reducing agent. So concentrated sulfuric acid cannot oxidize chloride into chlorine, which means I'll get the maximum percentage yield of HCl with sodium chloride. All right. On the other hand, we have HBr. Now, when concentrated sulfuric acid is reacting with HBr, being an oxidizing agent, it will oxidize bromide into bromine easily. Similarly, iodide ions also acting as a reducing agent. So when concentrated sulfuric acid is reacting with it, it will oxidize iodide into iodine. So concentrated sulfuric acid can easily oxidize bromide into bromine and iodide into iodine, which means with sodium bromide and sodium iodide, you will not get the maximum percentage yield of hydrogen halide. Instead, you will get the maximum percentage yield of halogens, that is bromine and iodine respectively. So that's the whole logic behind that. And let me write it. First of all, chloride is not a strong reducing agent. So H2SO4 cannot oxidize chloride into chlorine, whereas bromide and iodide are stronger reducing agent. So they can easily oxidize into bromine and iodine respectively. Okay, that's the end of question number 1. That seems a simple question, guys. Next, sulfur dichloride SCl2 is a liquid at room temperature. When SCl2 is added to water, misty fumes are seen and a solution is made that turns universal indicator red. Okay. Um, why SCl2 is reacting with water? Because sulfur belongs to period 3 and all period 3 elements have vacant d orbital, which is why they can easily hydrolyze with water. So due to the presence of vacant d orbital, they can easily react with water. All right. Now identify the type of reaction that occurs when SCl2 is added to water. Obviously, uh, this reaction is going to be hydrolysis. Name a chloride of a different period 3 element that is also a liquid at room temperature and pressure. By the way, period 3 element that is a chloride and is a liquid, colorless liquid at room temperature is going to be silicon tetrachloride, which has a formula of SiCl4. All right. When it is treated with water, because of the presence of vacant d orbital, it hydrolyzes with water, and obviously you will get white precipitate and a misty fumes of HCl. So examiner is looking for the name. So I believe we can write silicon tetrachloride. Okay. And that's what we have done in the class also. Let me show you the equation. When SiCl4 is hydrolyzed with water because of the presence of empty d orbital, it will turn to white precipitates of silicon hydroxide and yes, reacting with water, converting into white precipitates of silicon hydroxide and the misty fumes of HCl. Okay. So that was the reaction we have done in chemical periodicity, if you remember. So silicon tetrachloride is a period 3 element which can form a chloride uh, which has a colorless liquid at room temperature and pressure. And when it is hydrolyzed with water, it will give you misty fumes of HCl along with white precipitates of silicon hydroxide. By the way, I've told you in the class that this silicon hydroxide is further converted into SiO2. So either you need to write SiOH taken 4, that is silicon hydroxide, or silicon dioxide. Both are correct from examiner's perspective, all right? A molecule of SCl2 contains two SCl covalent bonds. Complete the dot and cross diagram in figure 2.1 to show the arrangement of the outer electrons in a molecule of SCl2. By the way, sulfur belongs to group 16, and so it has 6 valence electrons. Chlorine belongs to group 17, and so it has 7 valence electrons. So sulfur is represented by dot. So let me show you the dots here. 1, 2, 3, 4, 5, 6. All right, these are the 6 valence electrons of sulfur. Now chlorine has 7 valence electrons, and chlorine electrons are represented by cross. So it's 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 5, and then 6, 7. All right. So that's the dot and cross diagram of SCl2. That's an easy diagram. But you have to remember that chlorine contains 7 electrons. In valence shell, whereas sulfur contains 6 electrons in the valence shell. You must remember this information, which you have done in atomic structure. Now, examiner is looking for the shape of and bond angle of SCl2 by whisper theory. Whisper is valence shell electron pair repulsion model or valence shell electron pair repulsion theory, which we have done extensively in chemical bonding. So, guys, let me show you the diagram. This is SCl2. Now, this molecule has 2 lone pair and a 2 single bond. So 2 lone pair and a 2 single bond is going to give you 4. Let me draw the 4 lines. The first line shows s orbital. The remaining line shows p orbital, which means the hybridization of this molecule is going to be sp3. So whenever we have 2 single bond and a 2 lone pair with sp3 hybridization, angle is going to be 104.5 degree, just like water molecule. And obviously, shape is going to be band shape. Band shape or V shape or angular shape or crooked shape structure. All right. Solid magnesium nitride is a crystalline solid. Obviously, it is an ionic compound because it consists of only 2 elements. So it has a pure ionic crystal, guys. Reduce the oxidation number of magnesium and nitrogen in magnesium nitride to complete table 2.0. Magnesium Oxidation number of magnesium nitride. Ooh, magnesium is found in group 2 of the periodic table, which means it has an oxidation number of +2. And nitrogen is found in group 15 of the periodic table, so it has an overall charge of -3. So its oxidation state is basically -3. Okay. Let me calculate the oxidation state of nitrogen. So we have 2 nitrogen atoms, so let's say 2x. The oxidation state of magnesium is 2. We have 3 magnesium atoms, so into 3 equals to 0. The next 2x equals to -6. Then x equals to -6 by 2. Then x equals to -3. So that's the oxidation state of nitrogen. Let me calculate the oxidation state of magnesium. So we have 3 magnesium, so let's suppose it's 3x. Nitrogen has a charge of -3. We have 2 nitrogen atom into 2. Since the molecule has no overall charge, equals to 0. Then 3x equals to +6. Then x equals to +6 by 3. Then x equals to +2. So either you can get the oxidation number directly from the group number, or either you need to calculate it like this. So we have done both, so I've given you the both the formats. This is for nitrogen, and this is for magnesium. I hope it makes sense to you. Okay, next question is, magnesium nitride reacts with an excess of water to produce ammonia and magnesium hydroxide only. Construct an equation to describe this reaction. That's an easy task. Mg3N2 is reacting with water. I mean to say, examiner has given you both the reactants and both the products. You just need to balance this equation. So that's an easy task, I believe. So it's magnesium hydroxide and ammonia. So how many magnesium here? 3. So we need to put 3 here. How many nitrogen atom here? 2. So we need to put 2 here. How many hydrogen atoms now? 2 times 3 is 6. 6 plus 6, 12. So we need to put 6 here. And how many oxygens we have now? 6 oxygen here. And 3 times 2, 6 oxygen here. So equation is balanced. All right. Next, explain why the solution produced in the reaction in C3 has a pH greater than 7. Refer to the products of the reaction in your answer. Why the pH greater than 7? If pH is greater than 7, then it means solution is alkaline. All right. And solution is alkaline because we have magnesium hydroxide. Magnesium hydroxide is an alkali, and all alkalis donates hydroxide ion in aqueous medium. Just because of that, solution is alkaline, which shows pH greater than 7. Also, ammonia is given off, which is also an alkaline gas. So this will show the pH greater than 7. So we need to write both the points. First, magnesium hydroxide is an alkali. So it produces hydroxide ion in aqueous solution. Also, ammonia is dissolved in water giving you an alkaline solution with pH greater than 7. Okay. Boron nitride. By the way, boron has 3 plus charge and nitride has 3 minus charge. According to ninth standard, if charges are same, they will cancel out with each other. So the formula between these two ion becomes Bn. So that's the formula of boron nitride, which is a white solid, and that melts over 2900 degrees Celsius. This temperature shows that it has a giant covalent structure. Giant covalent structure. By the way, figure 2.2, part of the lattice structure of the crystal of boron nitride has been shown. Use figure 2.2 to deduce the empirical formula of boron nitride. By the way, Bn is the molecular formula as well as the empirical formula. Okay, so Bn is going to be the right answer. Bn. Okay, and that's an easy task. Suggest the identity of another crystalline solid that has atoms arranged in layers similar to that of solid boron nitride. By the way, this is hexagonal ring-shaped layer structure. All right, and these layers are held together by van der Waals forces, and these are the covalent bonds. Right now, we have the same structure of graphite like this. So graphite is going to be the right answer here because it has a hexagonal ring-shaped layer structure, and layers are held together by van der Waals forces. Okay, I hope it makes sense to you. So that's the end of question number 2. Let's move on to question 3. Define Le Chatelier principle. So in a closed container, not in a closed container, if a system in equilibrium is altered by changing temperature, pressure, and concentration, then the equilibrium will move in that direction that does minimize this effect. All right. Reaction 1 describe the reversible reaction. Reversible reaction are those which moves both in the forward as well as in the backward direction between yellow Fe3 plus and colorless SCN minus to produce this red substance or red aqueous solution. A mixture of Fe3 plus and SCN and this is at equilibrium at 20 degrees Celsius. The temperature of this reaction mixture is then increased to 50 degrees Celsius and allowed to reach equilibrium. Reduce the changes that occurs, if any, in the equilibrium mixture at 50 degrees Celsius compared to the equilibrium mixture at 20 degrees Celsius. Okay. So basically we have a change in appearance. Okay. C. Delta H shows that the reaction is exothermic. So for any exothermic reaction, if we increase the temperature, equilibrium favors towards left hand side. If equilibrium favors towards left hand side, obviously we'll observe yellow color because this is a colorless solution. All right. So yellow color. is observed. More yellow color is seen. Okay. Now change in the relative constant of FeSCN2 plus. Obviously, if equilibrium at high temperature shifts towards left hand side, the concentration of this ion becomes decreases. All right. The concentration of FeSCN2 plus decreases because equilibrium favors towards left hand side. Change in the value of the equilibrium constant Kc. You know, Kc is only temperature dependent. As long as the temperature is constant, Kc is constant. But you are changing temperature from 20 degrees Celsius to 50 degrees Celsius. And since the reaction is exothermic, this favors the equilibrium towards the left hand side, which means we have more reactant than product. So if we have more reactant, obviously the value of Kc is going to be decreases because Kc is basically the ratio of the concentration of product over concentration of reactant. If I'm saying if reactant concentration increases, obviously value of Kc decreases. All right. So value of Kc decreases because equilibrium favors towards left hand side. In another experiment, equimolar amount of Fe3 plus and SCN negative are mixed together and allowed to reach equilibrium. The total volume of the mixture is this. So we know the total volume of the reaction mixture, which is 25 degrees Celsius, which we need to remember. The equation is given, and in this equation, we have similar molar ratio between iron 3 ions and SCN negative ions. That's called thiocyanate ions, all right? So we have 1:1 ratio between these two ions and also these. So equilibrium mixture concentration is given for both the ions. Calculate the initial amount in moles of Fe3 plus added to SCN to produce this mixture. Okay. So first of all, we need to understand that the concentration of thiocyanate ions or thiocyanide ions is actually the original concentration of SCN minus and the concentration of SCN2 plus. All right. So this is the concentration which we have determined by using the initial value of this and the produced amount of this. And since SCN negative and iron 3 ions have 1:1 ratio, which means whatever the concentration of SCN negative would be the concentration of Fe3 plus ions. So if I need to find out, hold on, this is the first point, this is the second point. Second point is original concentration of SCN minus is equals to concentration of Fe3 plus due to 1:1 ratio. Okay. So I can write the expression in terms of Fe3 plus ions like this. minus FeSCN 2 plus. This is the concentration. Okay. I have to find out the initial amount of this. So we need to subtract these two values, or we need to add technically these two values. So in order to determine this, SCN negative plus FeSCN 2 plus, I need to add these two values. SCN is 1.30 into 10 to the power minus 3 mole per. So in order to calculate amount, I need to use the volume, and the volume is given in the question, which is 25 cm3. So 1000 cm3 of Fe3 plus contain 1.6 into 10 to the power minus 3 moles. So if we have 25 cm3 of the solution, the volume is going to be, the moles is going to be 1.6 exponent minus 3 into 25 divided by 1000. So it's going to be 4 into 10 to the power minus 5 moles. All right. And that's my answer. 4.0 into 10 to the power minus 5 moles. Calculate Kc for reaction 1 and state its units. Show your working. That's an easy task. Kc is basically the concentration of product over concentration of reactant. We have only FeSCN2 plus on the product side, and its concentration is given, which is 0.300 into 10 to the power minus 3. Let me plug in this value in the formula. 0.300 into 10 to the power minus 3 divided by the concentration of reactants. We have two reactants, all right, and both exist in 1:1 ratio. So both of them have the same concentration, that is 1.3 into 10 to the power minus 3 mole per dm3. So the value of Kc for this is going to be, hold on, 1.3 exponent minus 3 into 1.3 exponent minus 3 is going to be this. 0.300 exponent minus 3 divided by answer, you will get 177.5. So 177.5 is my answer. All right. Units, yes, units. The unit of product is mole per dm3. The unit of reactant is mole square minus dm minus 6. Why? Because if unit are same and they are multiplying, the power usually add in such scenarios. So this is also mole per dm3. This is also mole per dm3. If two values are multiplying together, the powers are going to add up, right? So the unit is going to be mole square dm minus 6. Let me cancel out these values. So if I'll cancel out, it's going to be 1 over mole per dm3. So the final unit is going to be mole inverse dm cube. So final unit is mole inverse dm cube. So that's the end of this question. Okay. Question number 4. Define enthalpy change of reaction. So enthalpy change of reaction is quite easy. We have done it. Enthalpy change occur When 1 mole of compound is formed, from its constituent elements, in their standard states, under standard condition. All right. Now, in the next part, iron is made when iron 3 oxide is heated with carbon monoxide as shown by reaction 2. This is reaction 2, guys. Table 4.1 shows the enthalpy change of formation data measured at 298 Kelvin and 101 kilopascal. Basically, this is under standard condition, okay? So, substance is Fe2O3. The value of formation is given. We need to write the equation. And remember, equation has to be for the 1 mole. And equation needs to start from the constituent element. So, Fe2O3. In order to make Fe2O3, I need two different elements. The first one is iron. The second one is oxygen. How many irons we have? 2 irons. So we need to put 2 here. And how many oxygen atoms here? 3. So we need to put 3 by 2 here. Under standard condition, it is solid, it is gas, and it is solid. That's the equation for the first substance. For the second substance, this is carbon monoxide. In order to make it, I need two different elements. The first one is carbon, and the second one is oxygen. Under standard condition, carbon is solid, oxygen is gas, and carbon monoxide is also gas. We have one carbon here, we have one carbon here, it's balanced now. We have one oxygen, we have two oxygen here. So in order to balance oxygen, I need to put half here. Okay, and the third equation is already given with its value. Now examiner is asking complete table 4.1 by adding equations with relevant state symbols to represent. That's what I've done. Standard enthalpy change of formation of Fe2O3, standard enthalpy change of formation for CO. Use the data in table 4.1 to calculate the enthalpy change of reaction in kilojoules per mole for reaction to show your working. So let me write the equation again. This is basically extraction of iron through hematite ore. That's the equation you have done in O level. All right, O level chemistry. So let me write it down again. Fe2O3 plus 3 carbon monoxide converting into 2 Fe plus 3 carbon dioxide. And we need to find out the standard enthalpy change of reaction. Since the formation data is given, so we need to start the thermochemical Hausdorff cycle by using the constituent elements. So from equation, I need these three elements: iron, carbon, and oxygen. Iron, carbon, oxygen. Iron, carbon, and oxygen. Iron, carbon, and oxygen. No hydrogen here. Oh, that's easy. Okay. Under standard condition, iron is solid, carbon is solid, and oxygen is gas. We have 3 carbon atom here, 2 iron here. So 3 carbon, 2 iron, and how many oxygens here? 3 plus 3, 6 oxygen. So we need to put 3 here. We know that if formation data is given, arrow needs to be upward like this. So we know the value of carbon dioxide, which is minus 393.5. By the way, standard enthalpy change of formation of elements in diatomic molecules is always 0, which is why its value is not given in this table. All right. Fe2O3 value is given, which is minus 824.2. Carbon monoxide is minus 110.5 multiplied by 3 because we have 3 moles. Now, in order to calculate delta HR, I need to make an arrow in the clockwise direction. Now, these three values are in the clockwise direction, which is why I'll take the values as I'll take the positive values. It's not in the clockwise direction, so I'll take the negative value and I will equate all the values with 0, right? So delta H naught R is positive plus minus 824.3 plus minus 110.5 into 3 minus 393.5, and I need to multiply by 3 because we have 3 moles, equals to 0. So the value of delta H naught R, let me calculate. 110.5 multiplied by 3, it's going to be minus 824.3 minus 331.5 plus 393.5 times 3. It's 1180.5 equals to 0. So it's 824.3 plus 331.5. Oh, my bad. Wait. 824.3 plus 331.5. So it's basically delta HR minus 1155.8 plus 1180.5 equals to 0. So 1180.5. So 1180.5 minus answer is going to be plus 24.7 equals to 0. So delta H by R equals to minus 24.7 kilojoules per mole, and that's my answer. Okay, I hope it makes sense to you. So my answer is exact 24.7. Okay. So that's the end of question number 4. Let's move on to the next question. Hydrocarbon. Hydrocarbon are substances consist of carbon and hydrogen only. Molecules contain covalent bonds. Covalent bonds are usually formed by the sharing of electron. Oh, surprisingly defined covalent bonds. Basically, sharing of electron in which electrostatic attraction exists between nuclei of two atoms and bonding pair of electrons. By the way, bonding pair of electrons, also called shared pair of electrons. Let me show you the information. Let's say this is hydrogen molecule. Okay, this is the nucleus of hydrogen atom. This is the nucleus of hydrogen atom. Now we have 2 electron in this formula. First electron, second electron. So this is called bonding pair of electron, also called shared pair of electron. This is nucleus, contain protons. So basically nucleus and shared pair of electron has electrostatic attraction. Electrostatic attraction always exists between oppositely charged ions. All right, always remember. A carbon-carbon bond in alkene is made from sigma bond and a pi bond. By the way, sigma bond is always formed through side-wise overlapping, through head-to-head overlapping of orbital, whereas pi bond is formed through side-wise overlapping of orbital. Let me write it again. Sigma bond is formed through head-on overlapping, also called head-to-head overlapping, whereas pi bond is formed through side-wise overlapping of p orbital, which is also called lateral overlapping. Identify the hybridization of the carbon atom in carbon-carbon double bond in an alkene. So whenever we have double bonded carbon atom, I've told you in the class, the hybridization is going to be sp2. Draw labeled diagram to show in terms of orbital overlap how the sigma bond and pi bond are made in C-C bond. Sigma bond is always formed through head-to-head overlapping of s orbital. So I'm going to make the s orbital like this. This is head-to-head overlapping of, or S as head-on overlapping. This is between carbon atom, okay? This is the s orbital of carbon atom. This is another s orbital of carbon atom. So both of them undergoes S as head-on overlapping, so that you will get the sigma bond. All right. And the basic diagram which we have done is basically like this. My bad. See, that's an alternate diagram for S as head-on overlapping or head-to-head overlapping. By the way, we have done this example in class, okay? But I believe this one is correct. And also, s orbital has a spherical shape, but I've made it slightly an oval shape because of the fact that whenever orbital overlapping takes place, these s orbital experiences pressure, which is why to minimize that pressure, they will turn to an oval shape structure. All right, we have done that format in the class, if you remember. Sigma bond. Sigma bond is always formed through side-wise overlapping of orbital. So side-wise overlapping of orbital is quite easy. We have done it in class. This is the pz orbital of one carbon atom. This is pz orbital of another carbon atom. So this is going to be the side-wise overlapping of p orbital. All right. Okay. By the way, this side-wise overlapping of p orbital can also be written like this. Okay. So that's the structure of ethene. And I hope it makes sense to you. In C, in electrophilic reaction involving alkenes, the pi bond of C-C bond is broken. Suggest one difference between sigma and pi bond that explains why the pi bond is broken in electrophilic addition reaction involving alkenes. In electrophilic addition reaction, electrophile add first followed by nucleophile. And since the pi bond of alkene is acting as a nucleophile, so it can easily react with the electrophile. All right. And pi bond is weaker than sigma bond, which is why during the reaction, pi bond will break first. So let me write it. Pi bond is weaker than sigma bond, and also it is acting as a nucleophile. So can easily react with electrophile. And why pi bond is weaker than sigma bond? Because the electrons of pi bonds are further away from the nucleus, whereas the pi bond of sigma bonds are closer to the nucleus. So sigma bond has a strong nucleus to electron attraction, whereas pi bond has weaker nucleus to electron attraction, which is why pi bond is weaker than sigma bond. Okay, and that's a very important point. I think we need to add this point also. We need to add this point also, because electrons of pi bond are away from the nucleus. Then sigma bond. Okay. Complete figure 5.1 to show the mechanism for the electrophilic addition reaction of hydrogen bromide to 2-methyl propene to produce the major organic product. Examiner is looking for the major organic product. That means it is an unsymmetrical alkene and an unsymmetrical reagent. So whenever unsymmetrical alkene and unsymmetrical reagent are reacting together, obviously we need to follow the Markovnikov rule. And in that, we will get both major and minor product. Examiner is looking for the major product. Obviously, in major product, I have to go for the most stable tertiary carbocation or secondary carbocation. Obviously, in this molecule, I'll get the most stable tertiary carbocation. Okay, so that's the whole background scenario of this. First of all, let me write the dipoles here. Slight negative and slight positive. As soon as the hydrogen becomes slight positive, the pi bond of ethene reacts with it. At the same time, bromine in the form of bromidine will remove from here. So H, C, H will remain as it is. Hydrogen is attached to this carbon atom, whereas this carbon atom has positive charge. So this carbon has positive charge with no hydrogen atom, which means this carbon is going to be the tertiary carbocation. And tertiary carbocation is more stable than secondary and primary. Okay. And that is going to be your intermediate. So now we have bromidines. Bromidines react with this, converting into major product, which is like this. Okay. This is going to be the major product because tertiary carbocation is more stable than secondary and primary. Okay, that's the end of this question. Okay. Question number 6, or we have 6 questions. B shows stereoisomerism. Stereoisomerism, and that's the structure of B. Explain what is mean by stereoisomerism. Stereoisomerism, compounds which have the same structural formula which have the same a structural formula, and molecular formula, but different arrangement of atoms in space, which is also called different spatial arrangement. Spatial, SPATIAL, spatial arrangement of atoms. Deduce the number of stereoisomers of V. Explain your reasoning. Uh, by the way, the first chiral carbon atom, this is the second chiral carbon atom, and also it is a double bond between the carbon atom. So if we have double bond and a chiral carbon atom, we need to apply 2 to the power n formula on the stereoisomers. We have 2 chiral carbon atom and 1 double bond, so I'll use 2 to the power 3, so I'll get 8 isomers. So I'll get 8 stereoisomers. So let me write it here. We have 2 chiral carbons and 1 double bond between carbon. So applying 2n formula, will get 8 isomers. Deduce the molecular formula of V. V, how many carbon atoms? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and this one is 13 carbon atoms. Okay, so we have 13 carbon atoms. How many hydrogen atoms? 3 plus 2, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, 20 hydrogen atoms. And how many oxygen atoms? 1, 2, and 3. Okay, next is name all the functional groups present in V. So first of all, we have ester. Okay, that's ester double bond or ester linkage. We have ketone, we have alkene. We have ketone and we have alkene. Okay. Next, figure 6.2 shows 2 reactions involving V. Okay, this is reaction 1. This is reaction 2. Reaction 1 using reagent T. In reaction 2, we are using reagent U. Okay, identify the role of reagent T for each functional group that reacts in reaction 1. So what is the basic change here? Oh, the ester will remain same. All right. Whereas this ketone is converting into secondary alcohol, which means reduction takes place. Also, it is an alkene. Over here, it is an alkane, which means reduction takes place of ketone and alkene. So I need the reducing agent. Okay, the reagent T would be the reducing agent. Both for ketone, and I must say that I'm going to use lithium aluminum hydride for ketone and hydrogen gas for alkene. Okay. So reagent T would be the reducing agent, and I'm going to use two different reducing agents. I cannot use hydrogen gas because it's not going to convert ketone into secondary alcohol easily. All right. Suggest the identity of reagent U in reaction 2, reaction 2, reaction 2. This is ester, this is also ester, ester will remain same. This is alkene, this is also alkene, alkene will remain same. The only change in reaction 2 is ketone is converting into secondary alcohol. Again, it's a reduction. And since it is a one-step reduction, so I'm going to use sodium borohydride. If you remember, sodium borohydride is a weak reducing agent, and its formula is NaBH4. Okay. Both functional groups in one molecule of Y reacts with an inorganic reagent to form one molecule of Q and one molecule of methanol, as shown in figure 6.3. So this is why when it undergoes an reacting with inorganic reagent, you will get methanol and Q. Methanol. I'll get methanol if this ester is going to be hydrolyzed. All right. So that I'll get the ethanol from this part of the molecule. So let me write the structure first, and it's going to be the very complicated one. Okay, this is pentagon. And this is going to be OH. This is double bond. And this is the structure of cube, guys. Okay. This is the structure of cube, guys. So that inorganic reagent is going to be the water molecule, because in the presence of water, the ester is going to be hydrolyzed. Okay. So this is called hydrolysis of ester. The reaction is called hydrolysis of ester. So whenever hydrolysis of ester takes place, we'll get carboxylic acid and alcohol are the products. Part of the mass spectrum of Q is shown in figure 6.4. Only peaks with M by E greater than 198 are shown. Okay. First of all, it's 100% abundance. That means this is molecular ion peak, because it gives the information about the molecular mass of the compound. So molecular mass is going to be 200 for this Q. And this is going to be M plus 1 peak. Okay. Calculate the relative abundance X of the peak at M by 201. Show your working. Okay, let me count the number of carbon atoms first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we had 13 carbon atoms. Now we have 12. One carbon is lost in the form of methanol. Okay. So we have 12 carbon atom in Q. So the formula is number of carbon atom equals to 100 over 1.1. Abundance of M plus 1 peak, which is not given, which we need to find out, over abundance of molecular ion peaks. Is the number of carbon atom is 12, 100 over 1.1 is fixed. Abundance of M plus 1 peak we need to find out, and abundance of molecular ion peak is 100. So value of X from here is going to be 13.2. Okay. I hope it makes sense to you. Q contain only hydroxyl functional group. Complete table 6.1 to show the observation that occurs when 2,4-DNPH or 2,4-dinitrophenyl hydrazine reagent is added to separate sample of Y and Q. Where is Y? This is Y, and it contains ketone, so it can react with 2,4-DNPH, giving yellowish orange precipitates. And where is Q? No, this is not Q. Oh, this is Q. This is B. Okay. So Q also has carbonyl group, ketonic group. So it can give you also 2,4-DNPH. Why not in Q? Why not in Q? Why not in Q? Hold on. Both functional group in one molecule of Y reacts with an inorganic reagent to form one molecule of Q and one molecule of methanol. Okay, Q. And where is Y? Am I doing any mistake? Q, Q, Q. Q. Y contain 2,4-DNPH. So you will get a precipitate of 2,4-DNPH. Q also contain this functional group. So I believe it also gives oh oh my bad, my bad. I've got my mistake. That's so bad. Examiner has given us a clue. It's not double bonded. It's basically only hydroxyl functional group. The Q contain only hydroxyl functional group. All right, and that's what I was thinking. What I've done in this question. Now I can compare these two compounds. It has a carbonyl group, can give you yellowish orange precipitate with 2,4-DNPH. It cannot. Okay, so no precipitate. So guys, you have to read the question very carefully. No precipitate or no reaction. Bad. Okay, now next question. Oh, calculation. Under certain conditions, 0.0020 moles of Q reacts with an excess of sodium to produce a total of 44.8 cm cube of gas at STP. Wow. STP. STP. At STP, any gas occupy volume is 22.4 dm3. Examiner is looking for the number of hydroxyl groups present in molecule of Q. Show your working. Now we have volume of gas. What we can do here is moles of gas equals to volume of gas over molar volume. So moles of gas, we need to find out volume of gas is 44.8 and molar volume at STP is 22.4. Oh, that's dm3. So I have to convert it into cm cube. So in order to convert it into cm cube, I need to multiply it with 1000. So it's going to be 22,400. Okay. Oh, 22,400. So now I'll get the moles. 44.8 divided by 22,400. So it's going to be 2 into 10 to the power minus 3 moles of gas. And you know how many moles of Q we have? We have 0.002 moles of Q. So from my perspective, moles of Q versus moles of gas. This is 0.002 moles. This is also 0.002 moles, which means ratio between them is 1:1. That means 1 mole of Q is giving you 1 mole of gas. So let's suppose Q has an OH group. It is reacting with sodium metal in excess amount, converting into RONA plus hydrogen gas. Okay. If it's 1 mole, obviously it's going to be 1 over, it's half. Okay. So if it is 1 mole, it is going to be 0.5 moles of hydrogen. If I have, okay, so if I need to produce 1 mole of H2, obviously this must be how much? 2 moles, right? Yeah, 2 moles of ROH. That means this Q contain 2 OH group. Okay. So according to the ratio, we have same number of moles. If we have same number of moles, that means ratio between alcohol and hydrogen gas is 1:1. All right. So 1:1. So if it is 1 mole, obviously hydrogen gas would be half mole. If I need 1 mole of hydrogen gas, obviously this needs to be 2 mole, right? And that's what we have done in the reactions also. So in order to produce H2 from here, this must be 2 mole so that I'll get 1 mole of hydrogen gas. Okay. I hope it makes sense to you. So compound Q or molecule of Q contain 2 OH group. Use table 6.2 to describe and explain two difference between the infrared spectrum of Y and Q in the region above 1500. So I need to skip the fingerprint region, which exists between 500 and 1500 centimeter inverse. So Y and Q, Y and Q, Y and Q, Y. So Y has ketone and Y has ester functional group. So ketone has carbonyl group. Y has carbonyl group, and it's exists between 1670 to 1740. 1670 to 1740 centimeter inverse. Okay. And which compound? Q. So Q has only one OH, and that peak shows 32 to 3650 centimeter inverse. So that's the one difference. That's OH group is present. Q contain OH group, and its peak exists between 3200 centimeter inverse to 3650 centimeter inverse. I'm not gonna use ester because I can use ester also. but Q doesn't have carbonyl and Y doesn't have OX, so I can distinguish these two from these two peaks only. So how much marks we have for this part? 2 marks. I think it's more than enough. I think that's the only. I can write one more statement. If Y do not contain OH group, it is Q cannot contain carbonyl group. All right. And I believe that's the end of this paper. Yeah. Thank you very much.